Welcome to the Aether Decoder. Today, we will dive into one of the most iconic thought experiments in quantum physics, created not to celebrate, but to challenge the foundations of a revolutionary theory, Schrödinger's cat. Erwin Schrödinger, one of the architects of quantum mechanics, proposed this paradox in 1935 as a scathing critique of the Copenhagen Interpretation led by Niels Bohr and Bohr-Heisenberg. His goal was to expose what he considered an unsustainable philosophical contradiction, the idea that physical systems exist in multiple states, simultaneously until they are observed. But after all, is the cat alive or dead? The thought experiment proposed by Schrödinger is simple in description, but profound in its implications. Imagine a cat sealed in an opaque box, along with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, a probabilistic event governed by quantum laws, the Geiger counter triggers, activating the hammer that breaks the vial and kills the cat. According to the Copenhagen Interpretation, until the box is opened, the atom is in a superposition of states, decayed and not decayed, and by extension, the cat would be equally in a superposition of being alive and dead. Schrödinger, however, did not propose this as a physical truth. His experiment was a reductio ad absurdum, or absurd reduction, a logical argument to expose what he saw as inconsistency in the extrapolation of quantum mathematics to the macroscopic world. The wave function, the central equation of quantum mechanics, describes probabilities, not tangible realities. For Schrödinger, the notion of a cat being simultaneously alive and dead was an absurdity that revealed the limits of the orthodox interpretation. The key to understanding this critique lies in the distinction between mathematical superposition and physical reality. The wave function, psi, the solution to Schrödinger's equation, is a statistical tool that lists all the possibilities of a system before measurement. For example, for an electron in a double-slit experiment, psi describes its probability of passing through one slit or the other. But this does not mean that the electron literally passes through both simultaneously. Superposition is a mathematical description, not an ontological state. The fundamental contradiction emerges when we try to extrapolate the quantum formalism to macroscopic systems like the cat in the experiment. The Copenhagen Interpretation, by postulating that the act of measurement causes the collapse of the wave function, psi, has generated epistemological debates about the role of the observer. Although Bohr and Heisenberg never explicitly argued that human consciousness is necessary for the collapse, as evidenced in their 1936 correspondence, archived at the Niels Bohr Archive, the conceptual ambiguity allowed for equivocal interpretations. Schrödinger, in Science and Humanism, 1951, vehemently criticized this anthropocentric fantasy, stating the wave function collapses not by the mind, but by physical interaction with measuring devices. However, in recent decades, this technical nuance has been distorted by pseudoscientific movements. Currents of quantum mysticism, as analyzed in the article Quantum Nonsense, Stenger, 2009, Skeptical Inquirer, have appropriated the jargon to validate spiritualist narratives, ranging from the idea that the mind creates reality to quantum therapies without empirical basis. These distortions, popularized by works like The Tao of Physics by Capra in 1975 and documentaries like What the Bleep Do We Know from 2004, turn mathematical abstractions into poetic analogies, ignoring the rigor of the scientific method. As Nobel laureate Anthony Leggett warned in the Quantum Weirdness Controversy, 2005, applying quantum logic to everyday experience is a categorical error, not a transcendental revelation. Thus, as physicist Wojciech Zurek explained in his work on quantum decoherence, 1980, the collapse does not require a conscious observer, but results from the irreversible interaction of the system with its environment. In the case of the cat, even before we open the box, the Geiger counter, the hammer, and the air inside the box itself act as observers, destroying quantum coherence, and defining a classical state. This leads us to a crucial advancement in modern physics, the theory of decoherence. Published in detail by Zurich in the Physical Review Letters in 2003, it demonstrates that quantum systems lose superposition when interacting with environmental particles, such as photons or air molecules. For a cat, with its approximately 10 to the power of 27 atoms, this interaction is so intense that the superposition collapses in nanoseconds. Thus, the cat is never alive dead. Its apparent superposition is a mathematical illusion, not a physical phenomenon. Schrödinger anticipated this discussion in his original paper The Present Situation in Quantum Mechanics in 1935, and he writes, "The wave function does not depict reality. It is an instrument for predicting experimental results." This instrumentalist view contrasts with the realism of the Copenhagen Interpretation, which Bohr advocated with the famous phrase, "Nothing exists until it is measured." But we also have more abstract interpretations, such as the one proposed in the Many-Worlds interpretation by Hugh Everett in 1957, which suggests that all quantum possibilities are realized in parallel universes. In this view, the cat lives in one universe and dies in another, without the collapse of the wave function. On the other hand, the objective collapse theory by Roger Penrose in 1989 suggests that gravity interferes with quantum coherence, preventing macroscopic superpositions. Both attempt to resolve the paradox, but neither is universally accepted. Today, experiments with mesoscopic systems, which are neither microscopic nor macroscopic, reveal nuances. In 2019, researchers from ETH Zurich published in Nature an experiment where a small crystal containing 10 to the power of 10 atoms was placed in a superposition of two vibrational states. The result? Decoherence destroyed the superposition in milliseconds, confirming that the larger the system, the faster it chooses a classical state. In conclusion, Schrödinger's cat is not a puzzle, but a reminder. Quantum mechanics requires us to differentiate mathematical models from observable phenomena. As physicist David Mermin said, quantum theory is an extraordinary tool for predicting experimental statistics. Demanding that it also describes reality is like demanding that a shoe play Beethoven. Dear viewers, I hope I have clarified an issue that, I must admit, causes me some discomfort when I see someone misusing quantum mechanics to support mystical narratives. I recognize that this confusion is not entirely the fault of these people, nor is it the result of bad faith. In fact, the main party responsible for this situation is the scientific academic paradigm, often aligned with globalist interests, that spread narratives convenient to their limiting purposes, thus restricting the advancement of technologies with emancipatory potential. Science, as Richard Feynman reminds us, a physicist who even spent time in Brazil between 1949 and 1966, harshly criticized the teaching of physics in Brazil. In his work, The Character of Physical Law, from 1965, he states it is not about ineffable mysteries, but about the search for testable answers. Thus, nature does not operate through magical dualities. It follows laws that, although complex, are deterministic in their mathematical formalism, as demonstrated by Schrödinger's equation, and stochastic in their empirical manifestations. According to Heisenberg's uncertainty principle, the human difficulty in formulating the right questions, an epistemological problem discussed by Karl Popper in The Logic of Scientific Discovery from 1934, does not justify resorting to supernatural explanations. As Carl Sagan warned in The Demon-Haunted World, from 1995, extraordinary claims require extraordinary evidence. Proposals that mix quantum mechanics with mysticism, such as quantum healing, or the idea that thought alters reality, not only lack evidence, but violate the principle of locality, Bell, 1964, and the thermodynamics of open systems, Prigogine, 1977. As for the ether, or more currently, the ether, its classical conception as a material medium for wave propagation was refuted by the Michelson-Morley experiment, 1887, and by Einstein's relativity, 1905. These facts, used by globalists to keep physics in a purely materialistic bias for many decades, are beginning to be reintroduced by modern theories, such as quantum field theory, which presents a non-material but mathematized background field, like, for example, the quantum vacuum, space-time foam, and even the so-called dark matter. Thus, advances in this area, such as Frank Wilczek's work on ether theories, Physics Today, 1999, do not validate mysticism, but deepen our understanding of the structure of the universe. Therefore, before invoking quantum energies or conscious universes, I suggest studying the experimental milestones. From quantum decoherence, Zurich, 2003, to non-locality theorems, Aspect, 1982. Physics doesn't need magic to be fascinating. Its beauty lies in mathematical precision and the ability to predict phenomena, like the Higgs boson and even nuclear fusion in stars. However, do not forget that these phenomena will also be reinterpreted in the future, based on ether science. As physicist Sean Carroll would say in The Big Picture, 2016, understanding nature requires humility to accept the unknown and courage to reject easy answers. Let's remain curious, get skeptical. Thank you for joining us. Comment, leave your like, and share with students and those curious about the world of science. Hugs, and see you in the next episode of Aether Decoder.